Welcome and thank you for standing by. At this time, all participants are in a listen-only mode. During the question and answer session, please press *1. Make sure your phone is unmuted and record your name for introduction. Today's conference is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn today's meeting over to Holly Kirkendall. Thank you. You may begin.
Thank you very much, and thank you everyone for joining us today. Looking forward to an exciting topic presented by Mr. Kale, who is our Fisheries Biologist here at the East National Technology Support Center in Greensboro. His topic today is low water crossings for livestock and equipment, planning for aquatic organism passage. There are no CCA credits today, but we welcome all of your questions at the end of our webinar today. So if you would like, you can enter your questions using the Q&A option in the menu bar. Just type in your questions and we'll do our best to get you an answer. Or if you want to hold your questions to the end of the webinar, you can ask those verbally through the operator. And with that, we will get started with Mr. Kale Gullett.
All right. Hello, everybody out there, and thanks for the introduction, Holly, and thanks to all of you folks for dialing in and logging on today. That up right quick. All right, so over the next 45 minutes or so, I'll provide an overview of aquatic organism passage at low water crossings. I won't have a lot of time to go into great detail about much of this material, so please feel free to contact me at any time to further discuss or get additional information on anything I talk about today. In addition, you'll see a number of citations from handbooks and journal articles on some of these slides, and please let me know if you'd like copies or web links so that you can get them on your own. This net meeting is the fourth associated with the Center presented over the last 4 years concerning aquatic organism passage. The first, part of a series sponsored by NRCS Biologists, was moderated by myself and included Scott Jackson, Cosmo Bates, and Dick Quinn. These national experts discussed passage ecology, culverts and tide gates, and fish ladders. The second and third, delivered by me during other monthly net meetings, covered largely the same material with special emphasis on passage ecology and tools relevant to the East region. I encourage you to consult these three presentations for additional basic information on passage ecology and techniques. They're archived online at the URL shown at the bottom of this slide, or I can send any by request. Today I'll focus on low water crossings and how to plan and design these structures to fit within landowner operations and minimize crossing effects on river function and ecology. In addition, I hope to highlight some elements of planning and design that will enhance structural longevity and may minimize maintenance and replacement costs. Low water crossings, or Fords, at least in the context of today's talks, are sites where farm access roads or other generally unimproved roadways cross watercourses. Their primary use is to allow landowners to access other parts of their operations with equipment and to provide livestock with safe crossing points. The primary goal of a low water crossing is to provide safe and stable stream crossings that don't negatively impact water and ecological quality while remaining stable across a wide range of flows. So a recurring theme that I'll repeat a few times today is this. Road stream crossings are meant to be static sections in the most dynamic part of the landscape. They often pose passage problems and impair stream stability. Although the theme of today's talk is aquatic organism passage, I'll spend much of my time talking about how streams interact with the landscape. My reasons for this approach are, first, that understanding how a river is supposed to look at a crossing is key to diagnosing the reasons passage and site stability might be impaired. Secondly, you'll need to know a bit about river mechanics to know why a crossing is a barrier and how to fix it. Third, using a geomorphic approach to assess passage condition is useful because we don't know the locomotive ability of a whole bunch of aquatic organisms. And finally, using a geomorphic approach to design and build crossings will usually increase longevity and decrease maintenance activities and lost access time to parts of a landowner's operation. In the administrative context, I'd guess that many projects involving road stream crossings would include the first two practice standards listed on this slide. The first, Standard 578, or stream crossing, is presently out for public review and comment as part of the standard revision process. The first criterion in Standard 578 calls for us to design the stream crossing to accommodate passage of all life stages of aquatic organisms in accordance with species requirements. In addition, 578 refers the practitioner to Standard 396, or Aquatic Organism Passage, for additional design guidance on projects where passage is a resource concern or a stated desire of the landowner. Although 578 contains a number of criteria that dictate the type, appearance, and design specifics of a stream crossing, I'd submit that using a geomorphic approach, that is, trying to place the site in its watershed context and designing a crossing to fit within that context to the fullest extent possible, will provide the best mix of passage conditions for all the aquatic critters we may encounter and long-term stability in the face of a full range of stream flow and the materials it carries. Road stream crossings are a common feature across the United States. For example, recent Forest Service estimates for forested landscapes in the eastern U.S. suggest that there are about 2 crossings per mile of improved forest roads. Although I'm unaware of similar data for private roads and trails, I would guess that crossing densities are very similar and may actually be higher. Most existing crossings, whether they're culverts under an improved road or low water crossings on unimproved private trails, were likely not designed and constructed with passage considerations as a central element of the design process. For the most part, the idea of building for passage at stream crossings is relatively new, only coming to the forefront in the last 25 years or so. Because stream crossings are intended to be stationary elements of a decidedly dynamic landscape, they affect a number of aquatic and riverine functions. Broadly, they affect many aspects of aquatic ecology, including species distribution and population health, and often impede sediment transport, woody material cycling, and elements of surface and shallow groundwater flow. From a management perspective, stream crossings need to provide safe, reliable access for landowners and the things they need to make a living, specifically livestock and various sizes and kinds of equipment, a way to get across a watercourse. I'm sure many of you have seen stream crossings that present barriers to migratory organisms. All animals, both aquatic and terrestrial, need to move for one reason or another throughout their lives, whether it's to reproduce, colonize new habitat, seek refuge from adverse flow conditions, or forage for food. Movement is a necessity. Daily, weekly, or yearly migrations are common and somewhat predictable for a number of organisms. Although most commonly known as fish passage in years past, the business of getting aquatic animals from one point to another is now being increasingly referred to as aquatic organism passage because of the wide range of animals for which passage projects are being completed. The title of Standard 396 was changed this year to reflect the broader purpose of many in-stream construction projects. So passage barriers can have persistent and significant effects to aquatic species. For example, a recent study in mountain streams in northern Japan provides an interesting example of the effects of fragmentation in riverine systems. Sabo or check dams have been built by the thousands in an effort to control sediment discharge and mitigate major damage from debris flows and landslides generated by precipitation, earthquakes, or volcanoes. These dams have been built for hundreds of years, but the biggest structures and greatest numbers have been completed in the last 50 years or so. They provide some protection from major sediment events, but only have a finite amount of storage capacity. They range in height from more than 100 to less than 5 feet, but their effects on white-spotted char, which are resident salmonids related to brook trout, have been dramatic. These fish exist as larger migratory individuals and small resident fish that normally interbreed. But Sabo dams are complete barriers that have isolated habitats and populations into many unconnected fragments. 2 researchers have shown that the probability of occurrence or survival is related to watershed size and that genetic and population problems can occur in as little as 30 to 35 years following isolation. In addition, these folks saw physical deformities on fish during field work that are usually associated with small population genetics. They've speculated that about 1/3 of the populations they studied will disappear in the next 50 years. Other studies closer to home in the Midwestern and Eastern United States highlight the effects of stream crossings on aquatic ecology as well. Warren and Pardue looked at a number of road crossings in the Ouachita Mountains in Arkansas and found marked population differences above and below crossings. They also suggest that undersized culverts and concrete slab low water crossings presented the most significant passage barriers to all species. Ben Letcher and his colleagues looked at a number of crossings in western Massachusetts and found that barriers fragmented local populations. They also completed a modeling exercise that suggested that local extinction could occur relatively quickly without replacement from downstream sources, in this case between 2 and 6 generations. Buska and Pockert looked at crossings in the Flint Hills ecoregion of east central Kansas and found that crossing type strongly influenced species passability and that crossing slope, length, and width, especially at low water crossings, had a profound influence on passage success. And finally, Keith Nislow and his colleagues, in a paper published a few weeks ago, looked at a number of crossings on the Monongahela National Forest in West Virginia and found that species composition and abundance above impassable crossings was half that found above reaches with passable crossings. So, restricting animals to small or isolated habitat patches by impairing migration has a number of consequences. Complete barriers can, over years, extirpate migratory animals in upstream reaches. Fragmented populations are more susceptible to serious decline or extinction, and reduced gene flow can lead to genetic problems that limit population fitness. Impassable crossings can affect population demographics, specifically diversity, abundance, and spatial structure. And finally, populations that are poorly distributed across your river basin have little or no buffer to catastrophe. Evaluating the effects a road stream crossing has on passage can be difficult. In a few cases it's obvious, like these kokanee blocked by a culvert in Idaho. But for the rest of the cases, those where there aren't any bright red fish blocked below a culvert, gathering information about the stream system will help you understand how a crossing affects stream and passage condition. Again, using a geomorphic approach will allow you to assess passage condition without a detailed knowledge of individual stream organisms, their mobility, or migratory habits. Quantifying the departure of a stream from its natural state, in quotes, will help you describe the relative passability of a stream crossing and provide insight into designing for aquatic organism passage. So climate physiology, physiography, and geography conspire to create watersheds, which is where we work. And identifying the factors that govern landscape condition is key to many of the types of work we do, and it's the same thing for aquatic organism passage. Placing a crossing within the larger context of its watershed will help you quantify the effect a site has had on stream morphology. We know that watersheds can be segregated into 3 component parts: headwaters, transfer, and depositional. Knowing where a given road stream crossing fits within this continuum will lend insight into a whole bunch of things, like average substrate size, channel gradient and plan form, the relative influence of vegetation on channel stability, and important species and habitats. Since the basic function of a river is to move water, sediment, and organic material downstream, we can classify the stream segment affected by a crossing as either a transport or response reach. Here's a good question to ask yourself the first time you visit a site. Is the main function of this reach to move material through it or to respond to the material delivered? So here's some examples of transport reaches in North Carolina and New Hampshire. Transport reaches are characterized usually by steep gradients, boulder and cobble substrates with pockets of gravel and smaller material, and narrow or non-existent floodplains. Channel morphology is often cascade or step pool types, and the banks and beds are durable because they're made up of big rock or well-embedded large woody debris. Bankfull channel indicators can be hard to find because some reaches in transport reaches aren't fundamentally alluvial. Many of these channels are composed of lag deposits left by landslides, debris flows, or glaciers, as in the New Hampshire photo. So stream crossings in these systems need to be steeply sloped and able to pass basically constant and periodically high bed load rates and large pieces of wood. Limited interaction between the river and its floodplain confines most high flow events to the channel margins. Channel changes associated with crossings are usually localized to the area near the crossing itself, extending up and downstream only a few channel widths. Virtually all other stream segments in a watershed can be classified as response reaches. Slopes can be locally steeped, but the major differences are seen in overall smaller substrate sizes, more complex channel morphology, and the common presence of a well-defined floodplain bracketing the river. Plain bed and pool riffle architecture, as seen in these streams in Tennessee and Maryland, is common. Substrates are mostly cobbles and gravels, and riparian vegetation helps govern channel stability, location, and geometry. Lower elevation response reaches usually have pronounced meanders and complex morphology, like this river in South Carolina, and include dune ripple channels such as this stream in Alabama, just a few feet from Mobile Bay. Substrates are generally small and in large supply, and large woody material loads can be substantial. Response reaches are where the majority of our customers live and work, and where we are most often asked to help. These reaches are sensitive to landscape and hydrologic changes within a watershed, and channel adjustments can be significant and fast. Consequently, crossings in response reaches must be designed with consideration for a wide range of channel changes with the potential to extend for significant distances up and downstream. These sites can be complex, but knowing the general tendency of a reach will help you identify the general trajectory of that reach with respect to geomorphic change. So taken as a whole, road stream crossings often impair physical and chemical processes that create and maintain habitat. They also interrupt sediment and wood transport cycles, alter shallow groundwater and surface water flow patterns, and can shift riverine habitat into areas more similar to lakes and wetlands. Since, again, these road crossings are meant to be static in a changing environment, it's a really tough standard to meet. And in many settings, especially where sediment and large woody debris loads are high, maintaining low water crossings can be difficult over time. However, looking at a few watershed factors during the planning and design phase can improve structural longevity and decrease the amount of maintenance necessary over time. So determining the watershed context of a crossing site helps you begin to quantify the potential stream flow, sediment, and debris transport regime that may occur at that site. Site geomorphology helps you understand a number of the design challenges you might meet and also provides insight into the type of structure that may best fit the crossing. In addition to knowing where you are within the watershed and its transport or response potential, it's also important to identify conditions that will affect channel and floodplain processes at your crossing site. For example, landslides can introduce huge sediment and debris loads into a channel. Active head cuts adjacent to your crossing site can migrate and endanger longevity. Analyzing the flow regime will help you characterize flow extremes that can affect passage and crossing dynamics. And further, the effects of a current crossing on stream morphology can be significant and will require consideration during the design process. Taken as parts of the bigger picture, considering these factors can help you diagnose present condition and put some error bars on the range of changes that may occur in the future under alternatives proposed for a stream crossing. At the site scale, the relationship between the active channel and floodplain is an important determinant in the suitability of the cross-section for a low-water crossing, and it also influences the type of structure installed. One useful descriptor of this channel-floodplain relationship is the entrenchment ratio, which is defined as the flood-prone width divided by the bank-full width. In areas where flood-prone width is difficult to determine from site factors, but bank-full is relatively well expressed, the flood-prone width can be estimated by extending the water surface elevation across the floodplain at an elevation equal to twice the maximum bank-full depth. The entrenchment ratio is a good index to the degree of incision of a channel, either as a natural component of the watershed or as influenced by past management activities or changes in the flow regime. As far as low water crossing siting and design goes, the more entrenched a channel is, the less suitable it is for a low water crossing. Although exactly quantifying the entrenchment ratio isn't necessarily critical for designing a low water crossing, It's useful to index because the degree of entrenchment at a site is an important factor affecting how steep the road approaches need to be, how sharp the vertical curve of the crossing will be, and how well the stream can be protected from sediment produced along the road surface and ditches. In general, more entrenched settings are better suited for culverts, bridges, and vented low water crossings. Less entrenched sites are well suited for unimproved or improved fords. Another aspect of considering watershed factors during the first phases of a passage program or individual project is to consider the use of formalized inventory and analysis methods. Formalized methods can help guide data collection and will provide some very useful information. In general, these additional details will help you quantify passage condition across a range of flows, prioritize crossing replacements within a watershed, initiate design, and approximate replacement or construction costs. Here's a great resource to evaluate passage at road stream crossings published by the Forest Service in 2005. Most western states have some form of a protocol for evaluating crossing, and some eastern states like Massachusetts, Maine, and Vermont have produced documents in the recent past. By the way, if you're interested in using the national procedure, the Forest Service recently completed a 30-minute online tutorial found at the website shown on this slide. It's a video primer that covers all of the data collection methods and techniques necessary to complete the procedure. In addition, the tutorial stops after each section and illustrates how to fill out the inventory worksheets. Although this primer is focused on culverts, many of the concepts are directly suited to low water crossings as well. Most inventory and assessment protocols require various field methods, and this guide covers the most common techniques, including basic topographic surveying, measuring channel cross-sections, and longitudinal profile measurement. I highly recommend this guide because it's clear and concise, and it covers many of the field methods and techniques necessary to analyze and design stream crossings. So, with some of those larger landscape factors in mind and maybe a few of those field guides in hand, let's move into a general discussion about low water crossings and then talk more about types and designs with reference to watershed location. Low water crossings or fords are often associated with historic sites and trails used by native peoples and early explorers. Generally, they're found at sites created by hydraulic controls like riffles or bedrock outcroppings that offer a uniform, relatively shallow spot that remains stable over time. This site, Fuse Ford on the Eno River near Raleigh, North Carolina, was associated with a mill and trading trail dating back to colonial times. Archaeological evidence from nearby sites suggests that this crossing was probably used by native people long before Europeans landed on the continent. Improperly designed and built low water crossings block aquatic organism passage, such as shown in this picture. However, like other road stream crossings, such as culverts or bridges, low water crossings can also pose a risk to livestock and equipment and cause chronic water quality problems. Low water crossings can be built with many types of equipment commonly found on farms. Front-end loaders or a blade on a three-point hitch can easily be used to push material around and into place across a stream. However, unless a ford is placed at a site that offers natural stability and built according to a few design principles that work with instead of against the stream, it may not persist over time. So before we get into some of the specifics regarding types and design elements of crossings, I'd like to mention what I think is another great Forest Service reference for designing low water crossings according to biological, geomorphic, and engineering considerations. This manual provides a comprehensive review and approach to methods used at a range of different low water crossing types with extensive design guidance and a great set of case histories. Although much of the information presented is geared toward road crossings larger than the types of routes NRCS is involved with, the guidance on site and structure selection, design and construction considerations, and fitting a crossing within a larger set of watershed factors is very applicable to what we do. So in general, low water crossings are built on low volume or unimproved roads on private lands. They're attractive because they're generally cost efficient and can be relatively easy to maintain. In addition, they can be designed and built to pass large sediment and debris loads with some efficiency. However, because they are a static structure in a dynamic system, they affect river mechanics and aquatic organism passage. So planning for passage on a given operation could be easily incorporated into our overall planning process. The nature and extent of a landowner's operations are key pieces of information needed to determine use and locations of crossings on a property. For example, an essential part of designing crossings involves knowing the types of equipment used on a farm and the number and kinds of livestock that might be using a crossing structure. The type of equipment used on a farm has a direct influence on the type and design of a low water crossing. We deal with a large range of different operations that use implements that vary in size, from big to small. In addition to considering the size of individual pieces of equipment, we also need to account for various other equipment and implements pulled by tractors and trucks. The physical dimensions, weight, turning requirements, and clearance of single vehicles and towing combinations are important factors that dictate crossing design requirements. One critical consideration I would like to propose during the planning process is a review of all road stream crossings on a property to determine whether or not crossings can be removed and consolidated to the fullest extent practicable. This is very much site-specific and requires a lot of cooperation on the part of the landowner. But removing as many crossings as possible while preserving the daily operations of a producer goes a long way toward improving stream health and function and preserving good passage conditions on a parcel of land. For example, here's an aerial image of a small farming operation south of Greensboro, North Carolina. The landowners have a mixture of pastures, hay meadows, and crops that all require seasonal movement of equipment and livestock, in this case cattle, between different parts of the farm, primarily from the barns and equipment sheds near the house. They presently use 4 stream crossings to access all parts of the property from the farm headquarters and spend some time on each one every year performing maintenance to keep the crossings clear and operational. Since the farm is bounded by county roads on all sides, at least 3 of these crossings could be removed if the landowner is willing to make changes to present operations by using existing roads to move cattle and equipment to different parcels. Outlying parcels where access via other means isn't available or feasible could be reached by consolidating 3 total crossings into 1 near the house because it's a site that offers better stability and less maintenance, primarily because of the physical condition of the stream. It's located above a bedrock outcrop at a natural gravel section and requires little maintenance over time. So this sort of planning obviously requires the input and agreement of the landowner, which is part of what we do, and may be affected by county ordinances concerning the use of roads for moving equipment and livestock. Granted, it's a simplified example with other workable outcomes, but the gist is to remove as many of the water crossings as possible within the context of the watershed and the daily operations of the landowner. So once you've done what you can to remove and consolidate crossings, it becomes a matter of selecting the type of crossing suitable for both the landowner's needs and the type and location within the watershed of the streams on the property. Here are some common types and categories of low water crossings in use today. The top 2 consist of simple fords located at naturally stable features or fords at similar control sections improved with materials that harden the travel surface. The middle 2 are known as vented fords and consist of a hardened road surface underlain by corrugated metal or concrete box culverts, for example. The bottom structure is a low water bridge where the road surface is supported by piers or spread footings with a natural channel bottom, and the structure is meant to be overtopped by larger flow events. As you may imagine, these things range in cost, construction requirements, and their effects on stream and passage continuity. I showed a couple of vented fords in the previous slide, and one metric that describes the effect of a low water crossing on stream function is the vent-to-area ratio, or VAR. VAR is the ratio of the constructed openings of a crossing to the bankful area of a stream. Low VAR crossings are those where the area of the vents is much smaller than the bankfull flow area of the stream. And high VAR crossings are those where the area of the vents is greater than or equal to the bankfull flow area of the stream. So in general, fords, high VAR crossings, and low water bridges all support good river function and passage. Low VAR crossings and other structures that affect sedimentation, debris dynamics, these things impair passage in much the same way as a culvert does. They create sections with shallow depths, high velocities, or elevation drops. The magnitude of these barriers often scales with stream size and flow. Often, the more improved a crossing is, the bigger a barrier it creates, assuming, of course, that the crossing wasn't designed specifically using passage considerations. So here's a couple of examples of low VAR structures. These crossings in Illinois and Texas are both jump, depth, and velocity barriers to migratory aquatic organisms. Further, they basically operate as flowhead dams and force a slack water reach above the crossing that affects stream dynamics. By comparison, simple, unimproved, or improved fords, such as this one in northwest Arkansas, provide year-round passage and can remain stable for years. Granted, they won't support the same equipment load as the two crossings shown in the previous slide. But fords like this represent a good number of the crossings that NRCS installs. Simple fords offer a good mix of construction ease, stability, safety for livestock and equipment, and generally work well with the stream over time. All of this equates to good passage conditions, good stream function, and minimal maintenance. So low water crossing design and analysis should roughly follow the same procedures I've outlined for stream simulation culverts in years past. In fact, the low water crossing document I mentioned earlier suggests the use of stream simulation techniques for low water crossings at high VAR structures as well as improved fords. Consequently, it's best to characterize the nature of the reach as either transport or response and account for the flux of watershed materials. Generally, crossings tend to function best when they are designed and built to conform to existing channel geometry and slope, constructed to match the shape of the existing channel, and oriented to cross the stream at a 90-degree angle. So cross-sectional geometry has a big effect on the type of crossing structure that's appropriate, will provide safe and reliable access for livestock and equipment, and will persist over time with minimal maintenance. The concept of channel entrenchment is useful here because entrenched channels require different structures than a relatively unentrenched channel. Entrenched systems focus flow, sediment, and woody debris in a small area. Stream crossings have to account for these factors in the design process to maintain stability and passage quality. So this table highlights some of the major site factors that are usually attributable to larger watershed processes that influence the suitability of 4 general categories of crossing structures, which are shown above the top as column headings. The 4 general categories are taken from the previous slide that I showed: unimproved fords at naturally rocky sections, improved fords outfitted with material that hardens the travel surface, high VAR fords with metal or concrete box culverts, and low water bridges. The table highlights the applicability of structures at locations affected by common watershed or site factors. All 4 categories provide some measure of passage and stream continuity, some better than others, and each is better suited for certain sites affected by watershed factors, channel geometry, or flow regime. For example, unimproved and improved fords are better suited for sites with flashy stream flow or very low base flows because they usually minimize changes to a channel cross-section as compared to high VAR fords or low water bridges. Conversely, using an unimproved or improved ford is usually not advised in entrenched channels or broad channels that move a lot of water at base flow. So I'll go over some examples of unimproved and improved fords, vented fords, and low water bridges in the following slides. Rock fords, whether unimproved or improved by the addition of rock fill or other materials that harden the crossing and support equipment loads, are commonly used in the eastern U.S. As many of you know, one of the most important design considerations associated with this type of stream crossing is placement. The best mix of passage and stability conditions will be found when the crossing is sited at a naturally stable section of stream. Bedrock outcroppings, riffles, or steps composed of coarse material are great locations for crossings. If these sites are found within the landowner's property, we can go in and improve the approaches, add material to the stream adjacent to or on top of the naturally stable section, and use fencing and gates to control livestock access. Design and construction costs can generally be managed to small figures, and sometimes on-site equipment and materials can be used to complete the crossing. Improved fords are generally constructed by opening up the stream above or atop a natural control and backfilling the cut with a well-graded mix of rock back to the existing bed elevation. Sometimes it's necessary to augment or improve the natural control with larger material. Depending on sediment texture and composition, it may be necessary to line excavated sites with geotextile to control seepage or cut off subsurface flow that might flow under instead of on top of the backfill. When rock is added to a crossing to improve the travel surface, there's a danger of building a sediment surface that creates passage problems because of turbulence or depth and velocity problems. In addition, if rock backfill isn't well graded, water can flow through instead of on top of the travel surface. So the best conditions for improved fords are usually realized when the backfill is composed of a mixture that mimics bed material as evaluated from a reference reach adjacent to the crossing, preferably upstream and away from any influence of an existing crossing that might have made the crossing section different from a reference reach or a self-formed reach. A good rule of thumb for getting away from the influence of a stream crossing is to move upstream at least 20 bankful channel widths before analyzing channel geometry and bed material composition. Moving this far upstream helps you get away from any existing crossing effects that alter channel geometry or bed form composition and spacing. In addition, it helps get you outside of what might be considered as the crossing maintenance zone, where equipment operations have affected channel metrics. Developing a backfill mix that approximates the natural bed material requires a bit of characterization with respect to the stream bed. More data is usually better, but a backfill mixture composed of at least 3 to 4 particle sizes usually provides good bed stability and passage quality. There's an awful lot of substrate analysis methods out there. The one you use is likely going to be a function of familiarity, maybe regional calibration or ease of use. But whatever method you choose, I would suggest that it's important to account for bed shape and particle diversity. You might consider developing your own roughness information if extensive modeling will be used, and that also helps you to gain a bit of insight into stream bed mobility. In addition, it helps to note features that force bed morphology. An important example of this would be boulder force steps and mountain channels. It also helps to investigate any watershed factors that control permeability or that are maybe a function of site construction activities like compaction or excavation that may interfere with shallow groundwater flow. For example, each of these unvented improved fords in Oregon, Virginia, and North Carolina match the channel shape and slope, cross at a right angle, and the bed surface is composed of materials that closely match the natural bed forms. Consequently, they've been relatively long-lived and provide good passage across a range of flows. The backfill mixtures aren't complex and can be created at a quarry or borrow site so that trucks deliver a prescribed fill mixture for direct placement into the section. You can also stockpile each size class on site and create the backfill mix using construction equipment at the site. Buckets on loaders or excavators can be used for measuring out rough composition, as well as on-site mixing before placement into the stream crossing. So here's a shot of an excavated crossing being backfilled with rock layers composed of about 3 size classes. Once rock is dumped in layers, it can be difficult to mix the material so that the resulting stream bed surface is well graded. At sites where passage is a primary project purpose, it's usually better to mix the backfill at a quarry or staging area, place it into the cut, and blend it laterally to the road approaches and up and down stream bed forms. Rock size and gradation should be the smallest mix needed to remain stable under prevailing flow conditions. Bigger isn't necessarily better for passage because of turbulence and can also create problems for livestock. You may need to add sand or soil into the mix to seal the section to ensure that the stream doesn't percolate into the crossing substrate. In addition, smaller material increases bed diversity, chokes voids between bigger stones, and helps preserve passage quality. It's also important to extend the driving surface of the crossing to an elevation that exceeds the known high water level. This design element is a criterion in the stream crossing standard. Keeping the crossing at grade, providing surface roughness, and ensuring that the downstream edge doesn't produce a sharp drop in water surface is the best way to keep material and animals moving through a system. So cable concrete or articulating concrete block fords are a cost-effective means to improve a stream crossing in situations where traffic volume, average load sizes, or the energy regime might be higher. They're usually made of 1-foot square concrete blocks connected to each other with light cable. Block mats are usually available in pre-made sections in widths of 4 to 8 feet and lengths from 8 to 16 feet. The concrete blocks are usually between a couple and 8 inches thick. Some come with a geotextile backing already attached, but if not, a layer of geotex should be placed on the prepared subgrade before the blocks are placed. Scour protection around the mat area is important, and this can be accomplished by placing a single row of blocks at least 6 inches below the finished subgrade around the perimeter of the mat. Unless the subgrade is uniform, smooth, and well compacted, the blocks can shift over time. Each block is independent of its neighboring blocks and can settle, rotate, or tilt. If this occurs, it can result in damage to the mats and a rough driving surface that may be dangerous to livestock. Once the blocks start to move, scour can endanger the longevity of the crossing. So, subgrade preparation is a key element of crossing longevity for cable concrete fords. So here's a few shots of a crossing project in Oregon showing a cable concrete mat and excavator prior to installation. Juvenile Chinook moving upstream between the blocks the day after it was built. And the crossing after the first rain-induced high flow event in the fall. Voids between the blocks can be backfilled with smaller material following construction, but they tend to infill naturally in streams with relatively intact sediment transport regimes. Here's a shot of a cable concrete crossing on a relatively steep transport reach in Wyoming where the mat wasn't extended up the bank line as high as necessary. In addition, the subgrade at this crossing wasn't well compacted because of the presence of large boulders. Erosion and settling at the site has exposed some of the structural cables, which can be a hazard to passing vehicles. It's rough to drive across, but functional from a passage perspective. However, sites like this where the blocks have begun to move around often fail over time. Another form of improved ford involves the use of concrete as precast planks or reinforced poured-in-place slabs across the stream. They can be relatively simple, but also more expensive than articulated mats or rock-hardened fords. They're durable and well-suited for systems with flashy runoff and high debris loads. Concrete slab fords offer a very stable, smooth travel path, but if the surface of the slab gets covered in algae, they can be very slippery to livestock. A smooth concrete surface can also be a problem for passage, but if the crossing is fully submerged and set to match stream gradient, passage can be satisfactory. Sometimes low-flow passage slots are incorporated into slab fords, but these can be pretty hard to maintain and tend to fill up with bed load. Passage slots sometimes self-scour at higher flows, but problems generally arise during low flows when deposition in the slots blocks access and organisms are forced to try and negotiate the slab surface. Okay, here are a couple of examples of concrete slab fords. This crossing uses hog slats on an ephemeral stream where passage may be possible at high flows. Here's a poured-in-place slab crossing in Arkansas that was submerged at the time of the photo but has a small drop along the downstream edge that might present a problem for weak swimming fish or animals that crawl. Slab fords can be a problem for passage again when the crossing surface is wide and flows are shallow and fast. So it's important to do all you can to design these things to be underwater at all but the very lowest flows. Another way to improve a ford is to use geocells or plastic cellular confinement structures. This technology is best suited for low gradient streams with bed material consisting of sand and gravel. As with some of the other approaches I've talked about today, the subgrade for a geocell crossing should be smooth, uniform, and well compacted. This requirement, coupled with the need to properly expand and place the geocells before filling them, means that the crossing site should be completely dewatered prior to and during construction. Geocells should be placed on geotextile and then backfilled with a mixture of small gravel. Finally, the cells should be covered with a mix of larger gravel, and the top of the crossing should be kept to the level of the natural stream bed. Keeping a cover layer on the cells is important. Tire damage can weaken them and result in elevation changes that may affect sediment transport, crossing stability, and safety for livestock and equipment when uncovered geocells become part of the travel surface. Here's an example of a geocell crossing, and you can see the cells at various areas along the ford. Although not presently an issue for passage, the long-term stability of this crossing is a problem unless the geocells are covered with a surface layer. And I'd guess that a bit more excavation at this site would have helped preserve cover at the crossing, improving its function for farm operations and passage as well. All right, vented fords are found in many locations across the Midwest and eastern United States, and most were built between the 50s up to about the mid-80s. These fords commonly consist of multiple small culverts set at or near the stream bed level that were covered with backfill and commonly capped with concrete or asphalt to harden the embankments along the upstream and downstream sides. Vented fords pass low flows through the pipes and are meant to be overtopped by high flows. Older vented fords typically have a low vent-to-area ratio and basically act like dams, causing upstream backwater and aggradation and sometimes downstream scour. Passage is often a problem because culvert outlets can be perched, and if not perched, often have high flow velocities. New approaches to vented fords that maximize the vent-area ratio offer much better passage and perform better across a range of flow, sediment transport, and debris regimes. High VAR fords can consist of bottomless arched culverts in smaller streams and multiple concrete box culverts countersunk and backfilled with stream bed material in larger settings. So here's a couple of examples of vented fords. This is an older ford in Missouri that illustrates a commonly constructed low VAR crossing. Multiple culverts set at different elevations are capped by a concrete layer that extends along both margins of the crossing to armor it from overtopping flows. Passage conditions are suboptimal, and although one of the culverts is fully submerged, velocities are fairly high. This example from the Ouachita Mountains in Arkansas shows a new concrete box high VAR ford that maximizes the channel area across the section and is bedded with natural stream substrates. Both passage and stream continuity are largely preserved in a crossing like this. The final example of low water crossing that I'll cover today are low water bridges. These are low bridges, and the deck or crossing surface is commonly supported by piers or spread footings. The elevation of the deck is set above bank full, yet low enough to be overtopped by larger floods. These structures are expensive, but as you might imagine, provide the best passage conditions and channel function of all the crossings I've covered today. Because they're used in larger streams and intended to be overtopped by large flows, low water bridges can be fairly robust and require a lot of excavation and concrete work. Given the costs involved, they're generally used on higher volume roads and are an attractive alternative to conventional bridges. Low water bridges need to be outfitted with some form of railing or curbing for safe vehicle and equipment passage because they're usually lumped in with standard bridges in the permitting context. However, because they're intended to be overtopped by high flows, railing designs can be tricky because of the need to balance regulatory height with passing debris. Here's a couple of examples of low water bridges. This one's in Montgomery County, North Carolina, and concrete footings support steel I-beams that support the single lane road. This crossing is on a national forest in Minnesota. It spans the active channel and a portion of the floodplain and uses concrete piles to support the concrete deck on a two-lane road. Each of these structures provides great passage and preserves a good bit of channel function and stream continuity along the road stream crossing. Crossing a stream at right angles is the best approach and is a criterion of the stream crossing standard. However, aligning a crossing and its attached road at a right angle to the downstream axis of the channel also creates runoff pathways that compulse large amounts of sediment to the stream system. Controlling approach runoff and sediment is best done by creating roadside and leadoff ditches associated with water bars or dips as far away from the channel and onto the floodplain as possible. In addition, and depending on site conditions like road grade, soil type, and expected rainfall, it also helps to extend road surface armor upslope to the nearest cross drain. Handling runoff and sediment before it reaches the channel will help protect water quality and may promote crossing longevity. Another criterion under the stream crossing standard calls for the use of fencing and gates to manage livestock use of the area. As many of you know, it can be difficult to maintain fences that cross streams. Sometimes a fence that won't get torn up by high flow and debris doesn't do a good job of excluding livestock, and fences that handle livestock well are often great at catching debris. These shots illustrate a cross-fencing technique that I've used in the past on projects that seems to do a good job of handling stream debris and excluding cattle. Sections of 1.5 to 2 inch PVC are hung from a cable stretched across the channel, and turnbuckles at the cable ends help tension it when it becomes stretched or if the posts sag or move a bit. Each pipe section is separated from the next by rubber hose or smaller PVC slipped over the cable as spacers, and the pipes can be cut to various lengths to match the channel's shape. These things swing when pushed by high flow and even provide boat passage in larger rivers. Gates for livestock control are essential because, given time, cattle will figure these things out and push on through. All right, one final consideration I'd like to cover today is crossing safety. I think it's important to emphasize that many of the techniques I've talked about are crossings intended for use under low water conditions. Things can get dangerous as flow depth increases at a crossing. Both lateral and buoyancy forces increase with depth, and muddy water can hide any scour damage that may have occurred during high flows. So taken together, these factors create potentially life-threatening conditions at flooded fords. Consequently, we should inform landowners about the dangers of flooded fords and include signage whenever we can. All right, that's all I have today, and I really appreciate your time and attention. I know I've blasted through an awful lot of stuff here, but before I turn this over to Holly, I'd like to mention another upcoming webinar I'm going to work on for delivery at the end of January 2012. The working title is Stream Habitat Management, Assessing Stream Condition, and Identifying Management Options. And with that, I'll now turn this back over to Holly and would be pleased to hear any questions or comments that you have regarding today's webinar.
Thank you very much, Kale. And operator, can you please come on and help us with our Q&A, please?
Thank you. We will now begin the question and answer session. If you'd like to ask a question, please press *1. Make sure your phone is unmuted, and you must record your first and last name slowly and clearly for introduction. To withdraw your request, you may press *2. Once again, for a question or a comment, please press *1 at this time. One moment while we wait for questions.
I would also remind our participants if they'd like to type in a question in the Q&A, we can certainly field those questions as well.
And I'm currently showing no questions. Again, as a reminder, it is *1. Unmute your phone and record your name for introduction. And it is *2 to withdraw that request. Again, if you have a question or a comment, please press *1 at this time. One moment while we wait for questions.
Well, we have one question about printing the presentation, and I would refer our participants to our new Science and Technology Training Library. In about a week's time, we'll have Kale's webinar and presentation up at the Science and Technology Training Library, where you'll be able to access those files directly and print or use as you need to.
And I'm currently showing no audio questions or comments.
Okay, one more logistical question kind of along the same lines about the replay. In just a few minutes, I'll show a URL that refers you to the Science and Technology Training Library. Plus, if you visit the East National Technology Support Center's website through the NRCS website, you'll find our webinars page there. So you could either do a Google search or you can contact me or Kale and we can help you get there. We've got one more question that was typed in. Kale, this says the North Carolina DOT requires culverts be buried 0.2
diameter.
Okay, and what is your recommendation for passage?
Well, first of all, thanks for the question. Countersinking culverts, you know, thank goodness we're starting to do that quite a bit more all over the place. My response to a sort of a uniform applies everywhere all the time embedment depth or countersinking depth is, you know, for me, you're really trying to maximize the pipe opening in relation to the size of the stream. Other factors like site slope, the crossing slope, bed material size obviously affect cover inside of the pipe. But the biggest, I guess, factor I've seen that promotes the best passage conditions and, you know, under which culverts stick around the longest is when you can put a pipe on there that matches bank full width as close as possible. So I don't know if that answers your question, but sometimes, for example, you know, you can get to a little bit wider portion of the pipe by sinking it a little bit deeper. So it's interesting that that they're requiring culverts to be buried at I guess that's 2/10 of the culvert diameter. But for me, again, it comes to trying to match that culvert opening, whether that's the span or rise or width, excuse me, to closely match the stream width. That's where you get the best bang for your buck, and they seem to stick around the longest and provide the best passage.
And I'm still currently showing no audio questions at this time.
Okay, well, I think that probably concludes our Q&A, and I'm going to pull up now the replay address that people were interested in. Again, this is kind of a screenshot of our new Science and Technology Training Library. You'll see the URL to reach the library below that image. Feel free to contact me or Kale if you're having difficulty accessing that site. I would mention that Kale's previous webinars are also uploaded to the library. You can go back through and view the webinars and see the presentations there. For our non-NRCS participants, you can get the replays by going to our public website that's associated with the NRCS website. We just mentioned in our regular monthly series, our next topic is crop diversity rotations and systems for soil health. That will be presented on Wednesday, September 28th at 2 o'clock Eastern. And our speaker is Ray Archuleta, who is a conservation agronomist here at the Tech Center. And with that, then we will conclude this presentation. And thank you very much. We had excellent participation today. I saw a high number of 185. Thank you much, everybody. Goodbye.
Yeah, thanks, everybody. Really appreciate your attendance. Bye.